Okay, so for this video, we're going to be talking about Chapter 5, which is a big part of Exam 3. And as you know, Chapter 5 focused on testing series, testing to see if series are convergent or divergent. And so there's this document here that I'm going to put in the week 15 module that you can use to kind of help you while you're reviewing. Now, you can't use this on the test, but this is the kind of stuff you should know when you're trying to decide what test to use. So the first question you want to ask yourself, you can see here, is the series a common series? So is it the P series, which looks like 1 over n to the P, or is it the geometric series, which looks like a constant times some common ratio r raised to the nth power. It could be n minus 1 power, but something that looks like that. So if it's not one of those common series where you can tell convergence or divergence easily, then the next thing you want to ask yourself is it alternating? Now, if it is alternating, but the alternating series test fails, then most of the time you're going to be able to use the test for divergence. That usually follows. Now, if you see that it's not alternating, remember to be alternating, it has to have like -1 to a power, right? If it's not alternating, then you're going to look to see if the test is easily provable to diverge by the divergence test, because that's an easy thing to take. You just take the limit of the terms and see if they approach some constant that's not 0. After that, then what I would commonly look for is to see if I can compare it, and usually we're going to compare with the P series, but sometimes geometric. So if we can compare, then we're going to use either the comparison test or the limit comparison test, but only if it looks like geometric or P series. Now, if it doesn't look like one of those, then you might want to use the ratio or the root test. These are also common ones, especially ratio. Ratio you're going to want to use anytime your series has factorials and or constants raised to the nth power. So, and then the last, you got the root test, which is when everything is raised to the nth power, everything in the series. And then if all else fails and your series actually looks like something that can be integrated, you can go ahead and use the integral test. So let's go ahead and look at some examples here. I'm going to go ahead and kind of put this off to the side. And the first thing is, if you're having trouble remembering what the different tests are and how to use them, you can look back in your notes. There's also a summary of the tests here in section 5.6, right before the 5.6 lab, right? So the 5.6 section has divergence tests, what geometric and P series looks like, comparison tests, limit comparison tests. It has all those tests and how they work right there. But what I want to do is look at the problems from question 2 on the 5.6 lab, because we did not do those. Those were not assigned as part of the lab. And so let's go ahead and take a look at those now. So if I'm looking at part A, I'm looking at that, I'm going, okay, so let's go through the common things here. Does it look like a P series? No. Does it look like a geometric series? No. Is it alternating? No, it doesn't have -1 to a power. Can I use the divergence test? Well, if you take the limit of these terms, you're going to end up getting 0 as your limit. And remember, in order to use the divergence test, you have to get some constant other than 0, or the limit has to not exist. And if you don't believe me that the limit is 0 there, you can go ahead and do that for yourself. I'm not going to go through that, but we can't do the divergence test. So can I compare? Well, looking at this, I mean, the main part of this series and what determines the values of the terms of the series are the n and the n cubed. Everything else is kind of not important. It doesn't have much of an effect. So if I kind of ignore the rest of it, it looks like n over n cubed, which simplifies to 1 over n squared, which is a P series. So that makes me think, okay, well, maybe we can compare. In fact, you might be able to see that right away without even asking yourself the questions we already asked. So what we want to do is we would want to compare what we have with n over n cubed, which is equal to 1 over n squared. And the question becomes, can we use regular comparison or does it have to be limit comparison? Now that the original series, those terms have a smaller numerator and a bigger denominator. So that means that side's going to be smaller than this side. And so, yeah, I'm not going to write out the wording here, but this works by comparison because our series, term by term, the terms are smaller than the terms in the convergent p-series 1 over n squared. So this is going to converge. And you want to go ahead and look back at the notes and see how to write that out. I'm not going to go through all that. Okay, so that's A. Let's go ahead and look at B. Again, does it look like one of our common series? No. Is it alternating? Yes, it is alternating. Now, what were the requirements? Remember, the first requirement is that the limit terms have to approach 0. Now, this is for the AST. Now, if you take that limit, this actually approaches 1, though. So, it's not equal to 0. The AST fails, but remember, if the AST fails, then usually we can use the divergence test. Just the fact that there's a negative 1 to the n power in there is going to make the limit of this thing bounce back and forth between positive 1 and negative 1. Because we know the limit of n squared minus 1 over n squared plus 1 was equal to 1. So if you throw the negative 1 over n in there, then that's going to make this limit oscillate. It's going to make the limit not exist. So it's going to diverge by the divergence test. All right. We can move on to C. Okay, so looking at one thing right off the bat I see everything right here is raised to an nth power. What is that going to tell us what test to use? That's going to tell us to use the root test. Root test. Anytime we have everything raised to the nth power, that's going to be the root test. Now, D, notice it's alternating. However, just looking at it, I'm not going to see that first requirement that the limit has to be 0. It's definitely not going to be the case. If you take the limit of that, that's like infinity over infinity. I don't know that that is the case. It's not obvious. However, you know, if you infinity over infinity, that means you could apply L'Hopital's rule. And actually, after applying L'Hopital's rule several times, I think you actually would get 1 over infinity, which would be 0. But another option for this, if you notice right here that we have a constant raised to the nth power, then that's an indication that we could also use the ratio test. If you used, and you can use the ratio test if we have alternating series, because when you take the ratio test, you find rho, and remember it's the limit as n approaches infinity of the absolute value of that ratio. So the absolute value gets rid of any negative 1 to a power. It gets rid of, it kind of deals with that alternating part. So you could use the ratio test. You could use the AST possibly, as long as the series are the terms are decreasing. I don't know. To me, that's just too much work for the AST, because to find the limit, we'd have to take the L'Hopital's rule like 4 times. And so to me, I see right off the bat, 4 to the n power, let's use ratio. The next one, if you start going through the list here, it's not a common series. It doesn't look like anything that I could easily compare with. It doesn't appear to be alternating. We don't have constant raised to the nth power. We don't have everything raised to the nth power. We're kind of running out of options. And so what I do see, though, is that if I were to integrate this, if I were to integrate from 1 to infinity, x squared times e to the negative x cubed, we could do a u sub and let u equal negative x cubed, which means du would be negative 3x squared, and we have the x squared. So that is a good example of the integral test. Moving on. Okay, we're going to keep moving ahead. Again, Looking for common type series. No, this isn't a p-series or a geometric. It doesn't alternate. However, even though it's not a p-series, it does kind of look like a p-series, because if I ignore that plus 1, then it looks like 1 over k times the square root of k squared, which is 1 over square root of k squared is k. This is 1 over k squared. So could I compare? Could I compare this with the original? And since the expression on the left has a bigger denominator, it's going to be smaller, and 1 over k squared converges. So this is an example of something that would converge by comparison. Again, you have to do all the wording there, but this definitely looks like something that might converge by comparison. Looking at G, again, you start going down the list, and I mean, just right off the bat, to me, I see, oh, well, this is mostly following square root of n to the fourth on the top and n cubed on the bottom. So if I were to ignore that stuff, I'd have square root of n to the fourth over n cubed, which is n squared over n cubed, which is 1 over n. That's the harmonic series, right? Harmonic, which diverges. And again, I'm going through this video very quickly just to kind of give you an overview. You need to explain yourself clearly. I'm just kind of talking through here. On the test, just like in the homework in the labs, I would expect you to explain clearly what's going on. This is comparing with a divergent harmonic series. So if I were to look at what I have originally, we know that when we're compared with the divergent series, it needs to be greater than, but we don't necessarily know that it would be greater than, just because this left side has a bigger numerator and a bigger denominator. So it's not clear that that's greater than or less than. And so in this case, since we don't know, we would want to use the limit comparison test. We would want to use the limit comparison test. So you want to go ahead and review that. We can go ahead and continue on. H, right off the bat, I see alternating. I'm probably an indication that I would want to use the AST right there. Hopefully that makes sense. It should be easy to show that terms are decreasing and that we have a limit that approaches 0 there. Continuing to move on. Don't have alternating here, but if you start to strip away the stuff that's less important, this is going to look like k to the 1/3 on the top over k times k to the 1/2, which is k to the 1/3 times k to the 3/2. And if you subtract 1/3 minus 3/2, I think this is going to simplify to 1 over k to the 7. So that's the p-series, right? So I'm going to let you decide there on whether or not you think that's going to be regular comparison test or limit comparison, but it does look like something we want to compare with. And then our very last one, I'm looking here and I see, oh, constant raised to the nth power. Let's use ratio test. And so that's kind of how I think of these problems. Kind of, again, in my head, I'm kind of asking myself these questions in this strategy for testing series. Again, I'm going to post this document. What I would recommend you do is when you have time before our test next week, that you go through these and you try to do each one of these. The answers were posted, right? The lab that we covered 5.6 in, all the answers for number 2 were posted, even though I didn't collect those answers. So you could go ahead and finish these problems off. This is also very similar to the type of problems that are in our review items in the week 15 module. So you have things like the practice exam, you got the Jeopardy review, you got an exam that I posted from previous semester. You got lots of opportunities to practice this stuff, and that's really the only way to get better is to practice. But I can't emphasize enough that you need to use proper terminology. You need to explain yourself. You can't just write convergent or divergent. If you do that on the test, it's not going to count. So reach out if you have questions. I definitely am willing to help if anybody has questions. And have a great rest of your day. Thanks for watching.